So to answer your question of how to set up a proof. So here is an example of a proof. So this is the thing I want to prove. I want to prove that n plus 0 is equal to n. So 0 is like the neutral element for addition. And so I write down the thing I'm trying to prove here. And then I enter proof mode. And intros is a tactic that will take the n and move it into the context as a hypothesis. So I should just use intro, actually. Yeah, so essentially what's going on here is this line, this horizontal line right now, doesn't have anything above it. But usually that's where you would see things you've already proved or assumptions you can make when proving this goal. So in order to prove that n plus 0 equals n for any arbitrary n, the way I have to do that is I have to basically say, suppose I have some n where I know nothing about it. Then I have to prove the theorem for that particular n. So that's kind of what intro does. It takes this n from the for all part here and just moves it up into the context. So now I just have some unspecified natural number n. And then the goal is now simpler, I guess. It's just n plus 0 equals n. So I skipped a bunch of the talk to get to this point. So it might help to just go back. But just to give you a feel for what it feels like to prove things in Coq. It turns out that if I want to prove that 0 plus n equals n, that's very easy to do. But if I want to prove that n plus 0 is equal to n, yes, that's easy because yes, but you'd have to prove that first. So just to show you how simple it is to go the other way, n plus 0 equals n, it almost follows from the definition of plus. So if I look at, so let's bring the n up into the context again. And now recall the definition of plus. It's doing pattern matching on the left argument, which in this case is n. Did I get that right? No, it's doing pattern matching on the right argument, I think. Let's just check it. We can actually print what plus is, which is called add here. And it prints, yeah, it's pattern matching on n. Okay. Oh, this is the failed. Sorry, this is the hard one. I got to scroll up to get to the easy one. Okay, now we're sane. So 0 plus n equals n. That's the easy one. So let's bring the n into the context. And so there's this tactic called simple, which essentially does like a call by name reduction on the term. So it just kind of does a little bit of evaluation. So what that means is plus here is a function that's defined elsewhere. And I can actually compute this because what plus does is it pattern matches on the 0. And when you pattern match on 0 in the addition function, then you just return the other argument. So a simple reduction shows that I'm left with n equals n. And how do I prove that? There's a tactic called reflexivity that will do it. So reflexivity is exactly. So it's easy to go in that direction. But now if we try to do the same kind of proof for the other way, where it's n plus 0 equals n, I run into a problem. So I do intro again, and I try simple, but nothing happens. Because it doesn't know how to reduce the n. It doesn't know how to pattern match on the n, because n is an arbitrary natural number, not a specific one. So I have to start over. And yes. So this is the definition of add, which is why it's easier in one way than the other, because it's like not a symmetric definition. Now, when I define the natural numbers, which I did at the beginning of the talk, I actually get this thing for free. This is the induction principle for natural numbers. So what this is saying is, if I want to prove that some predicate p is true for all natural numbers, I can do it by doing this. if I can show that it's true for 0, and if I can show that, assuming it's true for some arbitrary n, I can prove it for n plus 1, that's the successor of n. Then I can conclude it's true for all n. So that's how induction works.
So it's 0, then it's an arbitrary n, and it's another or the arbitrary plus 1.
Yes, so it's like, I prove that p of 0 holds without assuming anything. And then I have to prove that p of n plus 1 holds, assuming that it holds for n.
And n stands for induction, and there goes the rec, which is a recursion without dependent types, right?
Actually, they both have dependent types. So you can see that here's the rec one. So that's a type, but that's a term inside the type. So it's a dependent type.
But what is the difference between the two?
So watch as I go back and forth between them. So the first one is a prop. Now, set. That's the only difference. So it depends on what p I'm trying to prove. If p is like a predicate, and I want to prove it as a theorem, I would use nat ind, the induction principle. But if p is some, say, function that I want to, or the type of, like let's say I'm trying to recurse on a natural number, then I would use this one. This one. So it depends on like which world you're living in. Are we doing a proof or are we doing a program? In theory, it's the same thing, but in practice, in practice they live in like these kind of different universes. There's actually also these are both instances of something called nat rect with a t. Check, spelled it wrong. So now we have type here instead of prop or set. So to make sense of this, it's a little bit confusing because there's like this hierarchy of universes. I'll draw on the board here. Okay, so we have at the bottom types like nat, or predicates like even, let's say, even n for a natural number n. And the type of nat is set. The type of even n, I guess, would be prop. And the type of just even by itself would be nat arrow prop. And then these things live at, the type of set and the type of prop is called type. And now there's a weird thing going on here. The type of type, what's that? It's type, but it can't be, right? That's a logical paradox. That's like a well-known thing. So that we say this is type 0, it's type 1, and it goes up forever.
It's basically the full paradox. When you spell full, if you have a number, you have write it in English, and then the number letters it takes to write it, and then you go to that number, and you just repeat, or just repeat.
So 4 is like a fixed point of that function.
Yes.
So that's what's happening here. But when you see type without any like a subscript, then it's like there must be some subscript implied there, and Coq will have to figure it out for you. And another thing to point out here is that these universes are cumulative, which means that nat has type set, but it also has type 0 and type 1. So you can draw it like this, I guess. It's kind of nasty. Yeah.
Can I ask a super remedial question?
Yeah.
Even, just as an example, that's a prop.
That's confusing because it could also be.
It's as a prop, though,
Yeah.
it is asserting that it is even.
Right. So if I have
It's not like a function that tells you, is it even or not? It is asserting that it is.
Exactly. So a value of this type would it be a proof that n is even?
Yes, okay.
Yeah. Yes, it's kind of it could be either way. It's confusing. All right.
But that's the same difference here between nat in and nat rect. one of them lives in the prop space.
Yeah,
and
right.
one lives in the sense.
It's like parallel universe is kind of what's going on. The term universe is, I use that incorrectly because it's really referring to the vertical separation between these things. But you know what I mean, informally.
The one back up is the first type universe, and I'm assuming they kind of just repeats all other types.
And there's no real distinction between type 0 and type 1. It's just
It's just a number to keep track of, prevent paradoxes, yeah. So, so if I want to prove this direction, n plus 0 equals n, turns out to be much harder, as we saw before. So I'm going to start with the same strategy. I'm going to move n into the context as a hypothesis. And then I'm going to use this tactic called induction n. And what that does is it literally just calls this function, not ind. I mean, it sets up the types correctly so that, it prevents you from writing down some boilerplate. But if you look at this, this is a function. You can think of it as a function with a few arguments that you have to provide when you call it. So I've got to provide p, which is that's just the predicate that I'm trying to prove. And the induction, when I use the induction tactic, it automatically takes the goal and uses that as the p. So basically it's like, okay, that's going to be my p. And then what it's going to do is it'll actually generate just two subgoals for these two arguments here. And we can see that if I run it now. I have two subgoals. I can make this bigger. Okay. So I've got to prove these two things. Let's focus on the first one.
So couldn't the second goal you could drop out the
Let's show both goals.
basically the add one function whereas because it's on both sides of
So actually, it's not quite applied to the whole thing here. It's actually just applied to the n. So I can't cancel it out, unfortunately. If there were parentheses around the n plus 0 here, then I could just prove that the arguments are equal. N plus 0 and n are equal. But that's not the case here, yet. Although it turns out that it will be after some manipulation. So we start with this subgoal, which looks really easy, and it turns out to be. So I can do simple, which addition will pattern match on the first argument 0. We'll evaluate to the second argument. So we're left with 0 equals 0, and that's reflexivity. Okay, next subgoal. So this is the inductive step. Now I think what you mentioned there is exactly right. So if I run simple here, that's exactly what happens. So I guess the way addition is defined, it just turns out to evaluate this way. And now I can do exactly what you said. Although I don't need to, because I can just simply replace n plus 0 with n. I already have that proven as not proven, but I assume it as the induction hypothesis. So what I'm left with is Sn equals Sn. And I don't need to show that n equals n, because I can just say the whole thing already is reflexivity. S of n equals S of n. That's already
What is IHN stand for?
induction hypothesis on n. Yeah.
And so n is actually if you replace n everywhere with m, you would have to also change that to IHN.
Yes. Yeah. So Coq will generate names for you for these things unless you want to give them explicit names. And there's different schools of thought here about whether you should explicitly name all your hypotheses or not. Some people would say yes, you should, because you don't want to just rely on whatever Coq is going to generate. But there's other people who say, don't worry about that. You should actually focus more on proof automation and make sure that it's robust to whatever names they happen to take on. So that way you can change the names everywhere, and the proof will still type check. So
rewrite in this case, what is this? Does rewrite do? It seems to sort of magically do whatever.
It does seem like that, yes. So I have an equality. The induction hypothesis is like something equals something. And rewrite lets me replace like one side with the other. And I can also rewrite like this. And I believe the proof will still actually go through in this case, because I'm rewriting the, well, maybe not if it does both ends. Let's see what happens. Okay, no. But I can rewrite in either direction. So I could do that or that. But that's the default, so I could just leave that out. And if you want to go into how that actually works, we can do that. It's actually quite an interesting application of dependent types. So if I go back to, remember I was on, like in the other room when we were doing this talk, I was on this, I was in this file, and we were proving basic things with like propositional logic, like true and true, true or false. I didn't get to that one, but it's the same idea. And I defined or like this. And then at the very bottom here, I define equality. So actually, equality is not a built-in thing in Coq. I mean, it's in the standard library, so in that sense it's built in. But it's really just defined like this. And this is kind of a mouthful of a type to look at. So I think it helps to just really go through this slowly. So I'm defining a new data type called EQ. Okay, so proofs of this type are going to be proofs of that two things are equal. Now this is parameterized by the type of thing that I want to prove is equal. So that's what A is, which is just another way of saying that this EQ thing is polymorphic. It's not hard-coded to one particular, it's not like equality on integers or equality on strings or something like that. It's also parameterized by a value of type A. So, and there's another way to write this, which is perhaps more intuitive. So I could write it like this. I could take out the A from there and put it here. And then I could do for all x. So let's see. So that works too. So maybe this is one that's easier to understand, but this is actually not the one that's used in the standard library, but it's the same thing.
What is the difference in those two?
So for this particular type, there is no difference. But in general, there is a difference. So if I have, let me go back to the other one. Let's see. So this. So you can think of this as I'm defining not just one equality type, but a whole family of them parameterized by this x. So if I, like, for example, EQ of string of hello gives me a type. But EQ of string of world gives me a totally different type, two totally separate types. They each have their own equality proofs. But if I move x into here, I just call it like this, for all x. So now what's going on here is I don't have a family of types per se. I have a single type that's parameterized by these two things. And the difference is exactly the same as the difference between Gadgets in Haskell and regular algebraic data types. If you know what those things are, then I think that is the right way to think about this. So in Haskell, a regular data type would have the A's like over here. Like, just put it back to what it was. And it would actually have, so really I can't express this in Haskell because I have these two things. I mean, without Gadgets. Like with ordinary data types, I have x and y, but then they're not equal anymore. So that's a problem, right? So if I did this, now this is actually wrong because I'm allowed to prove that any two things are equal as long as they have the same type. Because I can plug in whatever I want for x and y. So
What if you put x on the second one?
You mean like this?
Yes.
Ah,
That's it.
so it doesn't type check.
Did it type check the other one?
What's this? Yeah, this is a valid type. It's just
sure.
not the type I meant to write.
Sure.
Yeah.
How does the difference map onto the type 2?
Say that again.
How does it map onto calculus and vector constructions?
Ah.
I mean, it seems like in dependent types here, there is no distinction as far as
No, there is a distinction. So, okay.
or maybe I'm just
Okay, let's see. So you can imagine this as like, actually this, okay, this, let me take out the wrong example because that's not going to help anyone. Okay. So in the calculus of inductive constructions, we can think of this as a function which takes an x and returns a type. And that's different than a type which is indexed by a term. So the type of the constructor ends up looking the same, and that's why this is confusing. Maybe that's one reason why this is confusing.
So it takes an x and returns a type.
Yes. In the way I've written it here, yeah.
The type takes another.
So okay, yeah, this is confusing. So the type itself doesn't really. It's like this A shows up in the types of the constructors here. But it's not really right to say that this is a, like, oh, okay. Well, maybe this, the most concrete thing I can say is that this A is allowed to be different in the different constructors, whereas this is not. So everything on the left side of this colon is the same for all the constructors, whereas everything on the right side can vary between the different constructors. So maybe if I write down a different example, like one that has more than one constructor, that might be better. Let me take this out. So imagine, okay, I'm going to duplicate this constructor. Say this is 1, these ligatures are hard to type with. Okay, now I can do, for all y, can I do that? Aha. So y is it's kind of like defined here, introduced there. So the reason I'm allowed to have x here and y here, and they're different, is because it's on the right side of this colon. That's talking about this A. However, now imagine if I flip them. So I do xx and yx. It should reject this. Aha. And the reason it rejects this is because for all of these constructors, this x has to show up there in this position, and it doesn't here. Because basically it's like, it's just a whole family of types that where each type is not allowed to like really have any different behavior depending on this thing. It's like a kind of an application of parametricity in a way. So maybe that's a way to think about it. It's like uniform types that don't, they do nothing with x except refer to it. That's a poor explanation, I think. It's almost like every constructor has to start with exactly these three things: EQ, A, Y, because these are all like that's like what shows up here. Yes, maybe.
Is there any way to see what it produces in the limit?
Good question. I don't know. This is kind of a weird bridge between Galena and the vernacular, and I'm not really sure about the interaction, actually. I can print out the types of particular terms like EQ, but that's not very helpful. Actually, yeah, it doesn't even type check, so let me go back to something that works. Okay. Yeah, so what happens when I do this? Actually, so that's telling me the type of it. I can print it. So this is the Galena. It's kind of just the same thing, yeah. So yeah, I think that's the only important difference. The constructors they can vary on this argument, but they can't on this.
And if it was an AGDA, would there be a difference? Sorry, this is really confusing because
yeah,
I'm not entirely.
This is totally confusing.
I define the same type in IBRIS, and basically we're completely different, right? So
oh, would it?
that's all three arguments exactly the same way.
Can it just can't do this? Does it just have like inductive data types? I'm not familiar with it, so I don't know. I would be surprised if you couldn't write this, though. Yeah, is there another way to explain this? Let's see. There's this common example of how to define a type-safe abstract syntax tree for a simple programming language using generalized algebraic data types, and you can't do the same thing with regular algebraic data types. And I think if we just Google, this example shows up in Wikipedia, and I found it was really helpful. Let's go to the Wikipedia. All right, so let's see. Let's zoom in on that. Maybe not that far. Okay, so so this thing that I have selected here. So here we have a data type that's parameterized on a type A. But this type A is not the same in these different constructors. So here it's a bool, here it's an int, here it's an int, and here it's a bool. So this is actually, it's impossible to construct an expression here which would be a type error if you were to like evaluate it some way. So in other words, like, let's see, what E equal is like a thing that takes two ints and returns a bool, supposedly in this language. So I can't even call it with anything other than ints. So that's something that GADTs let you do that regular data types would not.
Is there a way to get something that you give a bool that gives an int? If we had that function, we could use it to make it so that we can put anything in those.
Yes, you could. If you had additional constructors here that represent that capability, you could compose them. Yeah, that's right. So that's GADTs. I haven't found a lot of use for them in Haskell yet, but I use them all the time in Coq. So yeah, this type is it's probably one of the most confusing types ever. But maybe if we just move on and look at this proof, it might make some sense. So if I want to prove that 0 is equal to 0, what do I have to do? I have to call this constructor. I provide the type, which is nat, the type of the things I'm trying to equate. And then so this is the type of the thing. This is the proposition I'm trying to prove, and this is the actual proof here. And then so I'm trying to show that 0 equals 0. And the way I do that is I call the constructor EQ ruffle, which is this is how the reflexivity tactic works, actually. We can see that it has this type, which means that it doesn't have any premises except for the ones that are already up here, which are just nat and 0 for this x. And we'll notice that I only had to type 0 once, and it kind of gets duplicated here in the type. So it shows up twice in the type, but once in the term.
Because the sort of the left argument, so to speak, is sucked into the type. It's not part of the constructor.
Right. It's like the constructor gets to choose how to instantiate this A, whereas I have to choose how to instantiate this A. So maybe that's another way to explain it. It's like who's doing the instantiation? Yeah. Okay. It's a good way to think about it. Now,
It chooses one, you choose the other.
that's right.
Yeah.
Exactly right. Yes, that's good. I'm glad we had this session because now I'm going to use that to explain gadgets in the future. Okay, what I'm about to show you is a mess. It's going to be quite confusing, but it's quite enlightening to really digest it. So, a natural question that one might ask is, what kind of equality did I just define? Because there's different notions of equality. Like Coq actually has a built-in notion of equality called definitional equality. And so like 1 + 1 = 2 can be like, Coq can actually reduce 1 + 1 to 2 without any effort on your part or any rewriting or anything like that. But if I have 1 plus 1 equals using this equality 2, that's something I've got to prove. And there's different notions of equality, and one is called Liveness Equality. Liveness Equality is a fancy way of saying that two things are equal if for any proposition, or for any predicate, if the predicate holds on one, then it holds on the other. So that's Liveness Equality. And that's this type is kind of explaining what's going on here. So this is like a function. It's a function that lets you prove p of y, given all this stuff. And you know p of x. So basically what's doing is it lets you say, if I know p of x, and I know x equals y, then I have p of y. Kind of lets you rewrite, and in fact that's what this tactic, the rewrite tactic, is doing. It's like invoking this. And this is like some kind of complicated dependent pattern matching, where you could go into it if you wanted to, but it's not particularly enlightening to make sense of it. Really, the type says it all. And if we go down here, something surprising might, I think it's kind of surprising. If I look at the type of this Leibniz thing that I just defined, which is this, which it's pretty much just this stuff that I wrote here, and then I look at the induction principle that was generated automatically for this inductive equality type that I defined, it's actually the same. So really what Coq did is it wrote this for me. That's what it did. It wrote this function for me. So the induction...
It just says p of x. Oh.
Where are you looking?
Oh, I see that. I see both of p of y.
Yeah, so they both return p of y, I believe. So whenever you define an inductive data type in Coq, Coq gives you an induction principle for free. But it's not really built into the language. It's actually something you could define yourself. And Coq just happens to be doing that boilerplate for you. And here's an example of me defining the induction principle, which Coq defined automatically. It's kind of interesting that the induction principle for this particular inductive data type, which is meant to represent equality, is like this Leibniz equality function. So that's more deep than most people ever need to. When you're reasoning about just like doing everyday proofs, you don't normally have to think about this stuff. You just use the rewrite tactic and just like.
How are you going to do that?
Let's do that. That should be fun.
That would be very helpful in this case, because why the proof that is very simple. So 0 plus m equals n. That's very simple. If we can write this commutative property, we can just swap that and be like, hey, it's the same.
So this is so you're challenging me. I didn't expect to do any live proofing. So let's see how it goes. I don't know. We'll find out, right? Okay.
Does plus necessarily presume that they're naturals?
Yes.
Awesome.
So, yeah. So it's just doing type inference here.
Oh, sure. I would have told you that already, but I just wouldn't pay attention.
Yeah.
That's awesome.
So yeah, Coq's type inference is actually quite good for what it's doing. I mean, if you think about it, like to do type inference for a proof assistant really means you have to kind of do arbitrary computations at the type level potentially, and still I find myself writing less types than in Java. So that says something about, I don't know, how unnecessarily verbose Java is. Okay, so the first thing I'm probably going to do, well, okay, let's actually think about how would we prove this. So I'm guessing it's going to be like induction on n. That's something we could try. So one question is, do we want to bring the m into the context before we do the induction, or leave it quantified in the goal? I don't know the answer.
Basically, do you want to take out n?
Yeah, I'm not sure. So we can,
I think if you could take it out, m or n is, you just got m or n equals m or n. Basically, n equals m equals n. If you can take.
You want to do it in the right order, so you can use the zero trick for addition for the initial step.
Yeah, let's just try some stuff. I'll start out by not doing any generalization or specialization. Just try induction on n and see what happens. This is referred to as the video game approach to proving theorems, where you just try things, button mash.
That's what we call it type Tetris.
Ah,
Just keep trying.
Yeah.
It fits.
okay. So I've got this as my first sub goal. I have a feeling that I am going to have to go back, but let's try it out. So actually, I can use a lemma that I proved before. That's good.
0 plus n equals 10.
Yeah, but wait till I get to the inductive case. Okay. So let's what intro, simple, apply. What did I call it? Let's see. N plus 0 equals m. That's what I want. This one, n plus 0.
I thought you just did simple.
So I'm gonna do. Oh, I don't think. So simple gets me this far, but it.
Okay.
Remember, this is the hard one.
Oh, yeah.
Or is it? I don't know. But I can do
That's
this.
the hard one. That's the hard one.
Actually, not apply. I think I'm going to do rewrite this way. Oh, no. Other way.
Other. You know.
There we go. And then reflexivity. All right, great. So
And here it comes.
so I think this one's going to be a problem, but
Just use the definition of addition on the left.
let's just simple for the whole thing and see what happens. Let's do the intro, I guess. Get that m out of there. And then simple. Okay. So simple, I mean, it did everything it could already. But what happens if we use the induction hypothesis? We can do a rewrite, IHN. Okay. Now, yeah, just swap them.
Oh.
It's probably not helpful, is it?
Yeah, you can use the other way.
I wonder if I could do a. Wait. What I want to do is move this S out to the outside. I don't know how to get there.
You swap-
Could do,
you
yeah.
swap- you
Gotta make a
swap
lemma.
the N-
But I have a.
swap the S and N on the other side.
Yeah, did that.
Oh, but I can't do that on this side because I don't have m plus n. I have n plus sn, which is a different thing. I wonder if this is being recorded for YouTube.
It is, yeah.
That's not good news.
Well, they may stitch it onto the end as
That's not good news.
an appendix.
Just,
Up to you.
Just say a lot of swear words.
Just maybe they'll just bleep out the one part. Okay, yeah. What to do here?
This is fun, because it's hard to prove.
Yeah.
Because you want to co-induction. You want to
I don't think I need the co-induction.
You can't copy.
Oh, actually, with the induction hypothesis,
you're there, almost.
no, I can pick whatever m I want in the. So here, I can do. I think this is what I'm going to do. I'm going to say that.
You're,
Oh no.
no, you're inducting over
Oh,
here.
it sucks.
So you can't do that to the end.
Hmm.
Or at least I don't think you can.
You could set N equals Wait, why don't you just write a paper in the community copy? You just write-
Yeah. You should go ahead and do that, and then
I do have
I'll translate it into the cock.
Yeah. So,
I have no idea. Why don't we just go paper and then convert everything?
you worked on paper for a bit.
That's what people do in research. A lot of times they'll do the paper proof first because it's easier. They'll translate it into this.
Like on purpose.
Yeah.
I'm trying to prove commutativity of addition.
Yeah. You got any ideas?
I don't understand the syntax that well, but
How would you do it on paper?
No, we're fine.
Let's see here. Is this even the right? what I want to do.
That's all you.
I have it done.
But you want to do it inductively?
Yeah, I think you'll have to.
So for all n and m plus n is equal to n plus n, right? And then what's the inductive step? So,
That's what.
Yeah, that's where we are.
okay.
I want to be in the audience now.
You could subtract m.
We don't have that though.
You could subtract m from both sides. So,
We can't though. Because to be able to do that, we have to have the commutativity. We either have to have additive inverses, and we still need to.
So I can tell you one thing we could do. We could say search gnat. And what it does is it shows me all the stuff related to gnats. And I could, there's probably going to be some lemmas here.
That's free.
And actually probably the whole theorem is free.
Sure.
But let's see what we get. So here's some built-in stuff.
Plus associative.
Yeah.
Surely there's plus.
Yeah, it must be here, huh?
I think we can go to the standard library and see how they do it.
We could, yeah. I mean, if we find it here, we can actually just print out the definition
Oh, sure.
directly. Maybe it's not in the standard library.
Surely it's called plus.
Oh,
plus comma.
what's plus associative?
It was just one that went by. It was plus associative.
I mean, what does that mean?
It's associative. Repetition is associative.
So I can read that?
So you can put the parentheses here or there. You're adding three things.
I don't know.
Yeah, this is not very, it's actually not very helpful.
We could set the, we could find some way that s or the next equals plus 1.
Yeah, can we go back and do symbols and rewrite
You mean here in the subgoal, or do you mean
Yes.
go? So do simple, simple. Okay, yeah. And then
Wait, rewrite IHN is the same as cumulative.
But you can only assume that n plus n. You can only assume that that one limited sense.
So I can pick whatever m I want here, but I cannot pick n. That's the problem. So we might need a lemma.
But
Should we try to prove this as a lemma?
m could be 0. You could say
better
m is
mention
0.
But it's not always.
On m, you mean? Or on the sum? It's possible, but then I'd have to handle both cases. I don't learn anything from doing that because I don't know what m is.
Well, you could subtract.
Like I don't have any information about m.
Just question. Could you subtract n from both sides?
Subtract n from both sides here. Potentially, I'd have to use a
Well,
bunch of other lemmas to.
if m is 0, then just follows by simple.
Oh, I see what you're saying. So let's do a case analysis on m.
Yeah, I don't know how to do that.
Yeah, okay.
The identity would be base case, I guess.
So we can do destruct m. So destruct says, well, m is inductive type, or its type is inductive. It's defined by cases. So I'm going to just do case analysis. As long as I handle all the cases, then I'm good. So I handle the case where m equals 0. So I use a plus to go one level deeper in the bullets. Okay, yeah. So that helps us out here. So maybe I can do. I can use that lemma.
Or
The
just
n plus
simplify everything.
n.
I don't know if. Oh yeah. Great. Activity. Okay. So one subgoal remains. What happens if I simple this? That was kind of didn't really help. Successor plus 1.
Oh.
So,
That's sort of-
put it now, you put on the simple, and subtract m out, maybe? Because if you take out this last symbol, you got n, sm plus n, sm plus sm.
This is back when we started, so.
So what we could do is take out the outer s's, I think. But isn't that where we started?
Yeah.
Damn.
But can we apply that?
I think. Or can you
I don't
just
think
do
so,
an
'cause we can only-
In the second, in the induction step of your induction on n, do an induction on m.
So we could do another induction. We could try subtraction, but I have a feeling none of that stuff is going to be necessary.
Okay.
There's got to be a small proof for this.
Yeah.
One level of induction, I bet, will be enough.
But we have two variables, so to speak. We have two.
We do, yes. Well, so maybe, okay. We can. So it would be induction on
And you can
M.
destruct. Just induction on m without destruct.
Oh, okay, yeah. Oh, yes. So that'll give us an induction hypothesis
Yeah.
in the, yeah.
But we've already got most of it, I think.
I think this might be a fruitful approach. Okay, let's try simple.
Why plus and not minus?
Because minus means that I'm at the same like bullet point indentation as, like Coq treats these at the same level. So plus I'm going one level deeper, like with a nesting. And then the next one after that is asterisk. And then after that you use curly braces.
That's a piece of.
So asterisk.
So, oh yeah, so it says wrong bullet if I try plus. Because I didn't finish the goal I was working on. Okay, so reflexivity.
Using this.
And then,
Oh, yeah, we got it.
oh yeah?
Inductive hypothesis did it for us. Oh, no. No, not quite. Sorry.
You know what we can do? I think we can do simple in IHM
Yeah.
to make it look a little, oh, nope. I thought it would, oh, no, let's just do simple in the goal. Okay. Yes, so now I can use the induction hypothesis to rewrite. And there we're done.
Reflexivity. Yeah.
So addition is commutative. Good to know.
Woohoo!
We proved it!
Woohoo!
Double induction was the key. That was totally right.
And it makes sense because they're two.
Yeah.
Let's try on multiplication.
No, let's. That's awesome.
I think you might have to divide multiplication. Plus,
So division gets pretty nasty actually because so in Coq every function is total. Division naturally being not a total function. So we define everything divided by 0 is equal to 0 in Coq.
Well, division, it's not only is it not total, it's not closed.
Yes.
Which is, I mean, it's just a nasty function. We can stop it.
why not multiplication? Do we do subtraction?
Yeah, we can do subtraction. It's
So, could we define multiplication?
mm-hmm. Could define multiplication.
We could just do it and say, the result of multiplication is division.
But, so we're talking about natural numbers. So if I take 1 divided by 2, what natural number is that?
You say undefined.
Yeah, it's not closed. It leaves the naturals. Or it's partial, depending on how you want to go. So can you do all the proofs I've seen, and I've forgotten the language, but are, let me ask a question. Can you do proof by contradiction? Or is that
Yes.
not a thing?
You can. But it's actually a subtle thing because when people say proof by contradiction, they often mean one of two things. So, so in Coq, I can say, if I want to prove not A, so let's see, prove that. So that's not. Maybe I should
Prove it.
like.
Not what was that?
Okay, I'm going to prove that. So what I do is I can assume A and then prove false. So this is a completely valid thing to do in Coq and in general in constructive logic because of the definition of not. So not is defined that means like defined as. So say not A is defined as A implies false. So really, a proof by contradiction is exactly how you prove not A, because you have to prove this implication. And to prove an implication, you assume the input is given, assume A, and you have to prove the conclusion, which is false. So in a sense, every proof of not A is a proof by contradiction.
Okay.
However, sometimes another kind of proof by contradiction that people do is they assume not A, and then they prove false, and then they say, from that I can conclude A. That is not valid in constructive logic.
Great. Can you add it for propositions?
Say that again?
Can you add it as an axiom for
Yes.
propositions?
Yes, you can.
Is there a reason?
Yes, you can add this, and it's a thing that some people do. So actually, if you add this axiom, that's all it takes to get classical logic from constructive logic. But barring that, what you end up with is just proving not A. Oops. So this is not the same as A in constructive logic.
Clearly, its base use is constructive logic. Is that what most people use?
Yes.
That makes sense.
Yeah.
So you could make Coq just normal logic by adding one axiom
That's right.
that
And
he doesn't like, but hey.
Yeah, we try to not use axioms we don't need, and I've never needed this in all of my. I mean, I've only been using Coq for 2 years, and I've never needed it. There are actually a lot of different axioms you could add that are equivalent to this. So the law of excluded middle would be one of them. So if I say for all A or not A. So this is true in classical logic. It's like a given, but it's not provable in constructive logic. Yeah, so if I add this as an axiom, that's equivalent to adding this as an axiom.
I can show it's not true, maybe it's false. If I show it's not false, maybe it's true. But you have to explain the copy. That's how you prove the claims.
It can be like, if it's false, it's not false.
Can you show what kind of code it generates when you start to ask them?
Yeah. If I can remember the syntax. Okay, let's find a function. Like, say, neg b. Okay. How does it work? Extraction? Nope. I have to Google it. Aha. I don't want a recursive extraction. I just want a regular extraction. Do I need something at the top?
I love how it says illegal, not select. It says illegal. It says not it happened.
Oh, no. No.
It's illegal to do.
Require extraction. Oh, maybe that's the missing link. Let's put that up here. Where was it?
Right after
Oh, yes. Oh, there we go. Okay, so this is, I guess, OCaml, and I want to change it to Haskell. So I can say extraction language, I think. Yes, there we go. There it is.
and it realize somehow that your title is actually.
Yeah, there's some mapping somewhere that Coq uses. And you have to trust the mapping. because it's not like verified in any way. And you do a similar thing, like in Haskell, you would never define nat as like a 0 successor.
Could you extract a function on something with dependent types,
Ah,
just to see what happens?
okay, yeah, let's see. What has dependent types? Do I have any examples of this? That-
S-list is very short copy.
Oh yeah, that's right. Okay, let's take concat. See what happens. Concat, and I need the thing at the beginning. What was that? Require extraction. Okay, here we go. So, what did it do?
Explicitly passed. Didn't erase.
It did, yeah, it didn't erase the nats because they're not in prop, they're in set. So it kept them here, but they're just not used, I guess. Yeah, they're just extra arguments that are not used. One thing you could do, though, is you could define concat to have, instead of it taking natural numbers here, it takes like something in prop that contains natural numbers, like some kind of container, and then they would be erased. Ah, that's interesting.
Actually think that it's a little bit, definitely looks a lot more natural, which I mean, tactics, they kind of like feel
Yes,
a
and
little bit more natural than proving things and say,
it actually gets it gets quite magical when you start writing your own tactics. So I have I like look at some of the proofs that I've done. Maybe like, I don't know, system F soundness. So I proved the soundness of system F here in one line, and there's so much going on here under the hood. So eMagic is a tactic that I defined. Clean is a tactic that I defined. Induction is the built-in induction. And eMagic is actually referring to a database of hints that I've added for lemmas that I can use to prove this. And the total, I mean, it's actually, there's probably like a couple thousand lines of code that's being secretly invoked in here behind the scenes.
I think it's called magic together and mathematics.
So is this me? What is this?
Oh, so that's just or.
Okay.
Yeah.
So
Yeah. And then like this way would be and.
judge.
yeah.
Yep.
Thank you.
Oh yeah. Sure.
This is
I don't think this is kind of a talk, but also it's not a talk.
Yeah, it's kind of interactive live coding.
Like, what was this? Okay, let's try that.
Yeah, I was unprepared.
Do you have all of this proof somewhere?
Yeah. So the proof's here. So if I posted a link in the presentation.